Hi everyone, my name is Kyle Hartig. I am an assistant professor at the University of Florida in nuclear engineering, and I'm excited to be presenting my work on laser ablation spectroscopy techniques for nuclear applications. I'd like to acknowledge my PhD students, Kyle Laddie and Emily Clappis, who are major contributors to the work that I am presenting here. I'd also like to express my regrets that I was not able to attend in person as I unfortunately tested positive for COVID the day before I was supposed to fly out to join you all. But if you'd like to reach out with any questions or comments, my email is on the slide here. It's kyle.hartig@ufl.edu. So I'd like to take the opportunity here to acknowledge the support from collaborators and sponsors that my group has benefited from, particularly the DoD SMART Fellowship Program that's sponsoring my two PhD students that are highlighted here in this work, as well as the DITRA ERM Alliance and NNSA MTV Consortium. So I may go rather quickly through parts of my introduction as I'm aware that I am scheduled to follow Hari in the order of speakers. And he and I do rather similar work. He was my postdoc mentor. So I have a feeling he has covered quite extensively the basics of laser ablation and laser-based spectroscopy. As an introduction for my group's research interests, we're really interested in the fate, transport, and detection of nuclear materials following release into the environment. We look at the physiochemical properties of laser-produced plasmas and how they can be representative of high explosive nuclear fireballs, as well as the chemistry and spatiotemporal evolution of the expanding laser-produced plasma plumes. We're interested in studying actinides. Right now, a lot of our research is using surrogates. However, we have used uranium in the past, and we're working with our Savannah River collaborator, amongst others, to expand our research back into actinides. So this is where I might speed up a little bit, but the laser ablation process is quite simple. We use a high power pulse laser to vaporize a small mass of material, picograms and nanograms. This ablation process forms a highly luminous microplasma or laser produced plasma that is highly transient and sensitive to experimental parameters, environmental conditions. I list some initial plasma parameters that are typical for nanosecond and femtosecond laser ablation, as well as some of the diagnostic plasma parameters that have been reported extensively in the literature during times of which we see optical emission spectra. So I mentioned the spatiotemporal nature of these measurements. These measurements occur typically in the 10 to maybe around 100 microsecond durations, but we can use gated cameras to really narrow our region of interest in time to specific points in the evolution where we see either emission of discrete atomic, ionic, or molecular lines, and gating past this continuum emission where we have non-characteristic emissions occurring. So really looking typically for most of our measurements in the 100 nanosecond plus to hundreds of microseconds, depending on if we're looking at the molecular emission lines are focusing on earlier time atomic and even earlier time ionic emissions. So what does a laboratory-based measurement on radiologic materials look like using laser-based techniques? Uh, we have a representative spectrum here on the right side of the screen for a uranium plasma emission. This is a uranium metal sample that was heavily oxidized due to the pyrophoric nature of uranium and exposure to just the ambient environmental conditions. But we can see a lot of characteristic atomic emission lines as well as some ionic ones in blue and red respectively. The red ones there in the subset. We really have just more lines than we somewhat know what to do with, to the point that the number of emission lines are even causing a kind of artificial baseline increase due to their overlap. So even though there is very little background at the gating that we used for these measurements, the lines are blending together and raising the baseline kind of artificially. The objectives of this work are to study the different ablation techniques that we have available to us, whether that's nanosecond, femtosecond, or laser filament, for nuclear material analysis and studying the chemistry and dynamics of nuclear relevant elements in plasma plumes. You can see a picture of our laboratory in the bottom left with several optical tables, kind of have a laser source table in the back and an experiments table in the foreground, as well as a simplified schematic diagram of what in a typical LIBS experiment looks like, with a laser, some steering optics, focusing lens, collection optics, spectrograph, and computer analyses. I want to quickly highlight the two main routes in which isotope resolve measurements are performed with LIBS. The first is through the use of the atomic isotope shift that is transition dependent, which is usually also higher for large A number atoms. The second is the molecular isotope shift, which is primarily observed for diatomic molecules and will decrease with increasing molecular mass. So LIBS isotopic discrimination exhibits major shortcomings. These spectral shifts are small and they vary quite drastically for different elements. The magnitude of the isotope shift makes it difficult to separate due to Stark and Doppler effects observed in the spectra. And when optimized, most of these analyses are performed under rarefied conditions or inert atmospheres, and require a significant number of spectra to be acquired in the thousands typically. Molecular transitions benefit from a larger isotope effect. For uranium, we can see here that the uranium monoxide diatomic molecular isotope shift is about 3 or 4 times greater than that of just the uranium atomic isotope shift alone. So I alluded to this on the previous slide, but the molecular measurements benefit from the chemistry of the plasma expanding into the ambient environment. So unlike a lot of the atomic measurements for looking at different isotopes of LIBS, we're not operating under rarefied conditions or under atmospheres, and we're actually relying on the chemistry of the material to react with the ambient atmosphere to generate a molecular emission, specifically for uranium, generating a diatomic molecule, uranium monoxide, that we're going to try to observe the isotope shift in. We performed a lot of measurements with uranium under different atmospheric conditions, inert and rarefied. I'm showing just the kind of ambient versus rarefied cases here, and a kind of temporal waterfall, different gate delays and times, generally going to later times as you go up in these plots, to show the impact of the amount of air present in the sample chamber and its impact on the spectra, where we can clearly see that at later times a molecular transition is observed around the region in which Heaven and others reported in the late 80s a uranium monoxide emission line to be present. So we are fairly confident that we identified a uranium molecular emission related to uranium monoxide at this emission line that we could measure quite readily in our experiments. So like I said, we had several laser sources available to us, and so we looked at nanosecond and femtosecond laser ablation of uranium metals, see the difference in the spectra. Generally, the nanosecond plasma resulted in a higher temperature plasma, and at the delay time studied a little bit of narrow spectra. With the femtosecond plasma, a little bit of a cooler plasma, but due to the delay times, the optimized signal to background kind of resulted in a little bit more broadening being present from earlier time measurements to optimize how much light we were collecting. But we were successful in seeing the isotope shift in both cases for nanosecond and femtosecond laser ablation. We can even see some small atomic isotope shift in the nanosecond case with the narrower line widths. The femtosecond is a little bit more broad and difficult to see. This work was performed at Penn State. I'm the first author on it from part of my PhD dissertation. So how can you improve this? I'm pretty confident Hari is going to report on the 2D laser-induced fluorescence spectroscopy of uranium. This was work that Hari, Mark Phillips, my advisor Igor Jovanovic, and I did actually during the week of my PhD defense. I spent like a couple hours on my defense that week and about 50 or 60 hours that week working in the lab with Hari and others to perform this measurement on the natural and highly enriched uranium that we had available to us at the lab at Penn State. So we're using a tunable laser here to induce fluorescence in the uranium and scanning that narrow line width tunable laser across the transition uh, to see an enhancement in the emission from absorption of the tunable laser light as it crosses over first the 238 and then the 235 transition. So using a narrow line width source to sweep across these kind of small changes in the atomic absorption spectra and see a enhancement then in the emission due to fluorescence. So we can really see the power of this technique here for 238 uranium versus 235 in this kind of bottom left figure compared to the just passive Libs measurement in the bottom right figure B. There's some restrictions to how well this technique could perform in the field. I think Hari's made some improvements amongst others. This measurement was confined to inner atmosphere and I think a reduced pressure, if I'm remembering correctly. But regardless, it's a powerful technique that has shown a lot of promise for making isotope resolved measurements in a laser ablation plasma. So let's look at nuclear fireballs and laser-produced plasmas. First, we're going to look at laser-produced plasmas as a surrogate for nuclear detonations, and then laser-produced plasmas as a diagnostic method to characterize post-detonation nuclear environments. So laser-produced plasmas for fireball and explosives measurements. Our goal for this work is to understand the chemistry and physics that are occurring at a global and local scale within the plume, uh, as well as maybe the later time particulate effects, some of the agglomeration effects that may be occurring that we can study very easily in the lab versus might be quite difficult to do small scale physics experiments with out in the field using real explosives or other materials. So the similarity between laser-reduced plasmas and fireballs isn't just limited to the observed spectra, the species that are forming as highlighted on the previous slide. It's also the physical and morphological similarities that we can really explore here as well. This is an SEM image of a laser ablation event where you can see kind of towards the bottom right the actual crater from the ablation event, uh, a kind of sloshing of the ablated material out into forming a larger crater, a heat affected zone that's kind of burned and cleaned the surface of the sample, and you see kind of particulate distribution that was formed on the sample surface following this laser ablation event. So a lot of similarities to an actual detonation, and we can perform these laser ablation experiments to study maybe this particulate formation that's occurring that's relevant for forensics and fireball chemistry. Laser ablation techniques for plasma fireball surrogates, it really has to do with the ability to find similar temperatures and pressures and species being formed in the laser produced plasma at that specific time and under those specific conditions and compare them to actual high explosive or nuclear detonation events. And a lot of work has been done on this by the Lawrence Livermore group. Timothy Rose there is one of the contributing authors to a lot of the work, where they've really tried to match historical weapons test data to plasma surrogate sources available to us in the laboratory, like laser ablation or plasma flow reactors. And we can really see that laser ablation is a good surrogate for the cooling times slash rates, overall temperatures and pressures at earlier times in the fireball evolution compared to at later times where a plasma flow reactor might be a better source. So there is a significant limitation in the current research on the topic of plutonium nuclear fireballs using laser-produced plasma surrogates, very much just limited to a singular paper on gas phase plutonium oxidation by Harilal and others that you can see here on the bottom right. They visually identified possible plutonium oxide formation, uh, but cerium laser plasmas could provide a lot of insight into plutonium nuclear fireballs. Cerium is a common plutonium surrogate due to similarities in electronic, physical, chemical, and thermodynamic properties, as well as gallium-doped ceria is a better surrogate for weapons-grade plutonium. As for the species that we expect to observe for cerium laser-reduced plasmas, atomic and ionic cerium will be present and dominate at early times in the evolution of laser-produced plasma. As the plasma cools, chemical reactions will take place and molecular species will form. We expect to see cerium monoxide, which is characterized by signatures in the visible spectrum. Higher polyatomic oxides will also form at later times, yet signatures for these molecules typically fall at lower energies, thus will be outside the visible spectrum. So we'll be focusing on the early chemistry in this work. So just comparing cerium laser ablation plasmas to that of uranium plasma shown earlier. In experiments performed at Savannah River National Lab with our collaborator, Dr. Eliel Bilal-Aman, we can see the similarity in just the complexity of the spectrum, the number of emission lines, as well as the kind of drastic temporal behavior that is seen here between 1 microsecond and just 3 microseconds following ablation. So the first step in this work was to use LIBS to identify strong oxide bands in the visible spectrum that could be used to study the oxidation chemistry of cerium laser-produced plasmas. We can see here some pretty clearly identifiable oxide formation that's occurring over time, highlighted by the green and blue shaded regions, as well as some of the identified branches based on the available literature. Let's first focus on the atomic species. So as we increase the O2 mass fraction in the sample chamber, we see an interesting effect where at first with increasing O2 mass fraction, the lifetime of the cerium emission decreases faster, but beyond zero point 0.1 O2 mass fraction up to what would be ambient of 0.2, uh, we actually see the emissions start to live a little bit longer, i.e. the cerium atomic emission is shortest lived at a O2 mass fraction of 0.1, or about half of that of ambient atmosphere. So there's a lot of possible explanations for why this is being observed. One could be the increasing formation of cerium monoxide as the O2 mass fraction is increased. But then at higher O2 mass fractions, either we're limited based on the turbulent mixing that's occurring with the cerium metal plasma expanding into the ambient atmosphere, or there are other uh, consumption routes for the cerium or cerium monoxide that the increased O2 concentration is going towards. There's similarities observed in the literature for uranium and aluminum for this situation as well, and this is being further investigated. So if we take a look at the temporal behavior of the molecular species, uh, one, the cerium monoxide bands will become more prominent at later times over the atomic or ionic species, and you can kind of see that where highlighted in the green shaded region, one of the prominent molecular emission bands, and you can see around it a lot of the atomic species die away, and you get more of that characteristic sawtooth pattern for the molecular species. But we're also seeing a similar kind of effect of increasing mass fraction on the molecular formation uh, rate and amount of signal that we get to the atomic measurements on the previous slide, that the CEO intensity is optimized at a less than ambient O2 mass fraction, which leads us to believe that there's other molecular species being formed that is consuming CEO or atomic cerium with increasing oxygen mass fraction. What does this all mean for nuclear diagnostics? Well, what we've shown here in this work is that cerium is a well-suited surrogate for plutonium based on its extensive use for a number of physical and chemical properties. And in comparing the rate and amount of formation of different oxides and the decay of the atomic and ionic emission lines under different ambient conditions, we see similar trends to the extensive literature that is available for uranium-based measurements, either by my group or by other groups like Hartig's that focuses heavily on uranium oxidation. For the last part of my talk, I want to focus on plume detection with laser-based techniques. Our work is focused on femtosecond and femtosecond filaments and their interaction in low particle laden plumes. So we constructed a aerosol generator and dryer, this kind of orange cone-like device here in these pictures, and we passed the laser beam at the exit of this aerosol generator and dryer to detect different aerosols and particulates formed from ICP standard solutions, as well as kind of monodispersed silicate microspheres. We really threw everything we had in the lab at studying these aerosol plumes. We performed PMT, single channel, but temporally resolved measurements. We performed typical LIBS, optical spectroscopy measurements, as well as narrow bandwidth gated imaging of the plasma formation and expansion in these plumes. So when we perform PMT measurement of the ablated plumes, we were able to observe some of the effects that Hahn and others have observed for nanosecond aerosol detection with both the femtosecond and filament case, where you're not really seeing direct interaction with the particles and the laser beam itself. You're seeing the produced plasma in air following the laser ablation interacting with the particles in the plume. So the expanding laser plasma is really your sampling method, and that's where you're getting your signal from. And the PMT measurements really showed that we could isolate the kind of rare cases where we got a hit early on in time, i.e. the particle was pretty close to where the laser was ablating, or the particle got ablated itself, versus kind of here in the red in the upper plot, where the plasma expanded into a particle, which then caused emission to occur, which is seen at later times in the PMT measurement. So an interesting item to investigate for the plume detection is our sampling probability. So how often do we see spectra with characteristic emission lines of interest? And so for the three cases, nanosecond short focus and filament-induced breakdown spectroscopy, we took a large number, thousands of spectra, and developed an algorithm that would identify in each individual spectral acquisition whether or not that characteristic emission line was present. And for the nanosecond and short focus femtosecond libs, we had a very high probability of seeing a characteristic emission line of interest. But for the filament-induced case, we actually lost a significant number of our spectra due to not observing the emission line of interest. That can be due to a number of factors. In the imaging, what we're seeing is that the plasma size is just very small for the filament-induced breakdown case. We're not really generating a hot, dense plasma like we are for the short focus cases, and that's reducing our sampling volume and how well that interaction is exciting these emissions. You can see here in these images the custom vacuum chamber and aerosol generator and dryer apparatus that we have at University of Florida to conduct radiological plume measurements. So we can introduce uranium and other elements from liquid standards, generate aerosols, dry them, and introduce them into this chamber, which is a closed air loop, which can be vented through the fume hood or through HEPA filters, and then the fume hood, and perform our laser-based measurements on them. So we've done these measurements with cesium, and we've also repeated these measurements with the plutonium surrogate, as discussed before, cerium, as well as mixing different ICP solutions in different concentrations to kind of create a complex spectrum and start to elucidate, how well can we detect these different species and a number of other factors that we're kind of just starting to get into. So I'm just going to show some pictures of what some of these measurements look like. So this is a picture in our lab of us aligning a laser filament with respect to our kind of sample chamber where we have kind of pierced flanges that we affix to first align the device with. So we could replace those pierced flanges with sealed tubes and optical windows, and then flow either our plume through or backfill with a gas of interest and introduce short focused ablation. So using a 15 centimeter lens to focus tightly the nanosecond or femtosecond light down to a point, or use a loose focus like a 1 meter lens, focal length lens, to induce a filament to form at a position where we want to collect emission light from. I want to quickly highlight an extension of the previous work that was part of what we call the UF campaign, where Professor Igor Jovanovic and Dr. Milos Berger, you can see on the left image here, who are part of a DITRA and NNSA University Alliance, brought a tube of xenon gas that we were able to fill our chamber with and attach tubes to allow for filament formation within the dimensions of the chamber. And we're able to study plume interactions consisting of xenon gas and laser filaments. So I hope everyone enjoyed my talk. Again, I'm sorry I'm not there in person. Feel free to reach out to me over email. It's kyle.hartig@ufl.edu. But I hope my talk on some of the applications of laser ablation spectroscopy and techniques towards nuclear diagnostics was interesting. We're particularly excited about our plume tracking and detection efforts, along with the cerium work that is in collaboration with Savannah River. Here is a picture of me in the middle, my two PhD students, Kyle Laddie and Emily Quapis to the right, that were heavily involved in a majority of the work presented here, as well as my advisor, Igor Jovanovic and Milos Berger to the left of me, who were heavily involved in kind of the first part of this work. I'd also like to thank again all the collaborators that I have, some of which are in the room with you right now. With that, thank you. I'd like to thank you all again, including several of my collaborators that are in the room with you right now.